Yes, thank you guys for again uh, attending this session. Um, Offnote Labs, very quickly, uh, is a home for, so unlike having one slogan, we have two slogans. So it's a home for independent researchers and builders and senior researchers, helping young researchers to grow and shine. So essentially, Offnote Labs is a platform to do research without boundaries, and it, the two parts to research, as we view it, the mentors and the young researchers or young learners, and so there's no kidding and there's no PhD involved. Everybody who has a decent engineering background, and if our focus is on AI and deep learning, so uh, if you have a decent deep learning background, you can join the research program and work on very interesting cutting edge projects. And why do research? It might sound like a very academic thing to do, but the idea is that by doing research, and many of us who have uh, done research for a larger part of their lives would affirm to that research involves learning many skills, including flourishing in uncertainty, dealing with unknown problems and discovering your own ways of solving them, discovering your own taste of doing research, and at the same time aiming for impact. So you want to solve a problem that has significant amount of impact. The part to solving a problem which has impact is pretty long and hard. There's a lot of training involved, and Offnode Labs aims to bridge that gap and help you learn things in a focused way and do research. And one of the motivation why we build this platform is that with democratization of knowledge, archive, GitHub, papers around, code around, there's a rapid increase in number of eager and young learners who learn things on their own and play with code and build systems and write about it, publish it. And our belief is that well, we have seen that many of them rise to a particular level, but then they are stuck. And our belief is that with mentoring, they will further rise and shine, and without being part of a formal PhD or master's program, they'll be able to do very interesting research and contribute to the research ecosystem. So yeah, like there are two parts to it. One is we invite young researchers who are ambitious, who are ready to push themselves beyond their comfort zones and learn things quickly, go up on the learning curve quickly, and to learn and become experts under the guidance of mentors who we welcome to pursue research without any constraints of the particular place or the particular group they are part of. If they have interesting research topics to pursue, we welcome them and we connect them to interested young researchers who and under the platform of Offnode Labs, people can collaborate to do research. So that's it. That's a quick intro to Offnode Labs. The talk series is we are very happy to host Dr. Arvind Avanathan, Argonne National Labs, for this talk on drug discovery using AI and physics-based models. And this talk is part of the series Offnote AI talk series, and we have had a very distinguished set of speakers on talking on various sort of topics, applications of AI and deep learning, and I'm really looking forward to this talk. This is something that is a very treasured opportunity to hear about the cutting edge and drug design and discovery. You can check out our website, and our YouTube channel has previous set of talks. Okay, so having said that, I'll stop my screen sharing. And Arvind, please, if you can see that up arrow icon, you can click that to share. Yeah, and like I said earlier, this interface has, if you want to ask a question, there's a raised hand icon on the right. Please click it and I'll connect you to the mic. And if you want to just ask questions in the background, there's a chat box and you can type your questions. I'll be monitoring that. You can, and I'll periodically relay that to Arvind. Okay, sounds good. Again, very happy. Yeah, Arvind, all yours.
All right. Thank you so much. Thank you again for inviting me to give a talk on what we are doing here at the lab, as well as broader collaborations across U.S. and international borders. Um, this is by no means a work of one person. So it's an entire team of over 300 people. So I'm representing a bunch of people here, and you will see the names as they scroll along. I probably cannot represent everything that was done at the lab in terms of what we are doing with respect to SARS-CoV-2 research, but I'll try and cover as many points as possible. So this is going to be sort of an overview of research projects that have culminated in a bunch of different things over the course of several months now. So I'm mostly going to focus on how we are using artificial intelligence or AI in drug discovery against the SARS-CoV-2. And as Nishant said, I'm actually from Argonne National Lab. I also have a joint appointment at the University of Chicago within the Consortium for Advanced Science and Engineering. And if you're more interested in looking up some of the work that we do in our lab, you can go and check out our website. All right. So there are some real take-home messages from this talk. What I hope to convince you all is that AI and machine learning approaches can interface with rigorous physics-based models in order to address some real drug discovery challenges. And I'm going to present SARS-CoV-2 as a case study. My group in particular works on the interface of how to understand the use of machine learning in trying to understand some biological questions related to a class of proteins called disordered proteins. So that's been our main focus, and I'm going to talk a little bit of a vignette of what we are doing there, and mostly present SARS-CoV-2 as our case study. And we are looking to discover novel biological aspects of fundamental mechanisms of how the SARS-CoV-2 really infects a human being. So this is actually the first stages of viral infection that are guided by our AI-driven strategies. And so I'll talk a little bit about that. So this particular piece of work that looks at the first stages of infection was also recently awarded the IEEE Gordon Bell Award for use of HPC, or high performance computing, for COVID-19 research. So I'll summarize that very briefly at the end of the talk. And then I'm also going to present some views on our use of AI and ML approaches, how they pose interesting challenges in terms of how HPC resources need to be used, both on existing supercomputing platforms, which you might know come from the fact that we have CPUs and GPUs together. This is mostly the architectures of existing architectures, but also on emerging heterogeneous platforms, which I'll introduce you at the later stage of the talk. So that's all about what we are going to talk about today. And hopefully, it's kind of interesting and, engaging through the time. So I don't need to introduce COVID-19, I hope, to this audience. It was first discovered in Wuhan, which is a Chinese province, in 2019. It quickly spread out from there throughout the province of Hubei and then onto the world. Unfortunately, the problem with this virus is that it's quite large. So if you really think about this virus, it's about 100 nanometers in diameter. Usually viruses are between 60 to 70 nanometers in diameter, which is still a large virus. But these viruses are quite large, which is about 100 nanometers. And they are far more stable than what we know of SARS and MERS, which are also related to the same family of viruses, which are referred to as coronaviruses. They live very long on surfaces, and actually one of the problems is trying to understand how long they live and trying to characterize that. And the way this actually spreads is through close contact via respiratory particles. So there are lots of studies that have done fluid dynamic analysis of sneezing and respiratory particles coming out and trying to understand how long it takes for it to propagate and how exposure is needed before another person actually gets infected. Of course, that's a whole other story, but the idea is that it can be quite fast. you don't need more than 5 minutes exposure to actually get the disease. So unfortunately, it does spread very fast. And therefore, there is a very immediate need to kind of say, how do we understand, this disease in particular? Second, also to try and see how we can design drugs that can provide therapeutic strategies. Of course, the good news today is that we do have vaccines available, but the unfortunate problem, though, is that people that do get the disease need therapeutics that can actually help them. So if you look at this very enhanced picture of what the virus really looks like, it's a circular virus. It looks like a corona because there are things hanging out of it, which is called as the spike protein trimer. And the spike protein trimer is quite big by itself. It's about 10 nanometers in length and has around 100 copies per virus. And then you have the envelope protein, which is about 20 copies, and nucleoprotein, which is about 1,000 copies, and the membrane protein, which is about 2,000 copies. And all these proteins together just form the outer shell of this protein. And inside of it, what you see in these blue and orange coils is the genome of the virus itself. In fact, this figure is a very real representation gathered from experimental data from one of my collaborators on this project, which is Rami Amaro's group at University of California at San Diego. So once you take a look at all these different structures, you can start asking questions related to how many proteins are really present within the SARS genome. So there are a total of about 27 proteins that are coded by this virus, which is relatively a large number of proteins. And what you see here are these NSP structures, what we call as non-structural proteins, as well as what we call as structural or accessory proteins. So what I talked about in terms of these structures, including the S protein, the envelope protein, E protein, M and N, all these proteins are just part of the outer envelope. The spike is usually referred to as the S protein. And there are a bunch of other proteins that are like good targets for building medicines against. So these non-structural proteins are mostly involved in viral replication. They're mostly involved in viral entry. They're involved in all sorts of processes within the whole viral life cycle. And therefore, each of these proteins can actually constitute very good drug targets. So as a consequence, what we have done with our collaborators at Argonne, in fact, one of the directors of the Advanced Photon Source, which is our light source for taking X-ray crystallographic structures, we worked very closely with him, and we were able to access some of these earlier structures of these proteins, much more than other groups could actually access, because these were proteins that were first, crystallized in our labs, and therefore we could actually take a look at them, earlier than other people could. And so that offered us this idea that we could come up with a strategy to design small molecules that could be staged on this, what we call as a multi-stage workflow. So this is a project that's funded by the Department of Energy as part of what is called as a National Virtual Biotechnology Lab, or NVBL for short. And the idea behind this is to exploit artificial intelligence and machine learning techniques in such a way that we can enhance the performance of both regular simulations, as well as the idea of finding small molecules that can actually lead us to identify these things in a very short while. So the goal of this project, essentially in a nutshell, can be said as we want to do enhancement on regular MD simulations by up to 100x, or 2 orders of magnitude, followed by docking calculations, which can be improved very quickly. And I'll talk about all of these stages as we go along in this talk. The idea essentially to distill down, how do we take billions of molecules? So if you look at the estimated chemical space for drugs, it's about 10 power 60. This is the lower end of this margin. It's actually estimated to be about 10 power 68. So if you remember the Avogadro number from chemistry, this is about 6.23 into 10 power 23. But this is at least, several orders of magnitude bigger than what that is. So in terms of that, given this very large set of compounds that you're playing with, the idea that how do we search billions of molecules to find drug candidates almost becomes a very, very important point for trying to target these proteins. So, in terms of our pipeline, we actually started out by looking at what are the machine readable data sets that we can go after. Unfortunately, for drug discovery, there are not a whole lot of libraries that are open source, but also provide you with access to small molecule features on which you can actually compute. And what we mean by compute is essentially identify features from the data, which can include bond orders or other features that we care about a given molecule. At the same time, also try and understand how these things can be filtered for some of the things that we are interested in, namely identifying drug candidates for this proteins. So, of course, a lot of these libraries are out there. For example, there are about 4 billion known molecules that are accessible, including from Enamine, Drug Bank, Binding DB, e-molecules, and so on. And they actually provide you with access to all the chemical structures. But the unfortunate problem, though, is that these structures are not represented in a standard format that machine learning algorithms can readily digest. So, in fact, one of the first things that we had to do was canonicalize all these features, compute them in terms of what they constitute. Some of them happen to principal component analysis so that we can get the eigenvalues and things like that, as well as identify fingerprints so that we can do similarity searches and then generate images on which we can use convolutional neural nets or other artificial neural net sort of things. So this is actually, if you just imagine on 4 billion compounds, if you have to do this, you need large computing resources. In fact, we spent nearly 200,000 node hours in terms of computing across multiple platforms in order to get it to a process where we could actually release the data. So this constitutes one of the first release of HPC computed features of drug screening, which has about 23 input data sets, 4.2 billion molecules, 60 terabytes of open represented data on which you can compute. So if you want to take a look at it, you can actually download all of the data. We have canonical representations for most of these molecules, 4.2 billion represented molecules, moderate descriptors, which are basically all the features that you care about a small molecule, which is all present here, across 420,000 CSV files, molecular fingerprints, which are all coded in binary, and also 2D images, which are all pickle files on which you can directly compute. So obviously, there's a whole lot of data which use nearly 2 million core hours actually on all of these machines. So this computed data actually provides the critical input features that we need for these AI models to be able to predict. And this was led by Ian Foster's team at the lab. In fact, he pushed many of his PhD students as well as postdocs and other people to stand up this database so that we could actually query that on demand. So that's one piece of the story. A second piece of the story is also to pay attention to what we call natural language processing. And why is that actually important? So the moment you think of literature, there is a lot of collection of these molecules already present. So somebody has seen something that is related to this virus. We would obviously want to know what they are. And one of the things that you immediately realize is that in order to do this at scale, you need to have a way to, have these algorithms seeded with something that the machine learning algorithms can be trained on. So for example, we need training data on which we know what constitutes drug molecules, what constitutes treatment patterns, and things like that. And so some of the admin staff within the lab were actually involved in that. So we sort of crowdsourced this entire activity to the lab admin so that they could help us annotate a lot of these texts. So we extracted over 800 molecules and structures from these. And then we applied our supervised machine learning models to go and play on these COVID-19 papers data sets, which is also openly available, and built a named entity recognition model that could extract drug references from the entire corpus. So my group has also done quite a bit of work on understanding natural language processing techniques. especially for medical text and record. And you can freely play with some of these code as well as the training data and the tools that we have built as part of this project. Now, the real fun begins, which is to say, how do we screen these billions of molecules so that we can actually find drug candidates?
So, Arvind, if I may quickly ask,
Sure.
so there are multiple components to this, and not a lot of people might be familiar with biology. So there's this literature, medical literature, where these drug names are mentioned. As, so you need to run extractive algorithm on top of that, and then there are these molecules. Their shapes are candidate molecules are there. Their shapes are well defined. They're in a particular format. So I'm trying to just create the whole picture. What are the pieces of the puzzle which have to be, extracted together? And then there's this feature generation from the molecules.
I'll actually come to that shortly. So this is all the raw data preparation steps, really speaking, right? And then the fun part of this whole story is how do you put that together in this workflow that I was talking about? So I'll definitely come to that very shortly. Okay. So now once you identify a whole bunch of these molecules somehow, you need to identify whether there is something that is interesting or not. And that's actually coming to our computational workflow, where we are thinking of ways in which we can understand, with respect to these protein structures that I was showing to you earlier, what are the most complementary molecules that would bind to these structures. So that aspect of it is unfortunately not very direct. So if you look at a drug discovery process, this process actually takes billions of dollars and takes over 25 years normally. And we had to compress that somehow to get to a point where we actually have lead molecules within a short span. So for that purpose, we had to come up with ways in which we could do what we call as high throughput docking. And docking is usually the first stage, which allows us to basically say whether a small molecule with all the features that we've had before would allow us to dock that molecule to the protein receptor or target of interest. So that is usually virtual screening. There has been so much of effort on virtual screening in the last 30, 40 years that it's almost impossible for us to actually go and build something from scratch. But as I'll highlight a little later, there are some intrinsic computational problems with these high throughput docking studies, and then we'll see why we need better methods. And then once you do the docking, you need to do something which actually allocates or estimates what we call as the binding affinity. So given a protein structure and a compound that binds to it, we need to understand what is the complementarity, but also try and understand the energetics involved, which is to say, how does this molecule interact with the protein of interest? And again, there is a bunch of problems associated with it, which is that calculating this binding affinity is highly error prone. And therefore, there is a lot of doubts around these methods in terms of whether they're useful or not. And then you have this idea of saying, okay, once you get a hold of all these molecules, then you can actually go into try and estimate what is something very physically calculatable, what is called as a free energy estimates of binding. So starting from the docking step all the way to this, you have a huge computational pipeline where you have a multi-stage protocol, where first stage, you do a high throughput ensemble docking to identify molecules, what we call as hits. And then you have to thread it together with machine learning based molecular dynamics simulations, which is basically solving Newton's laws of motion on every single particle that you have in a system. But that can get very expensive very quickly, so that you can understand the mechanistic changes involved in the protein as a consequence of binding the drug. And then you have to do binding free energy calculations to basically optimize whether these molecules are really good or not. But at each stage, you have some computational bottlenecks, and we'll try and understand that one at a time. So the simple question is, why not take all of these 4 billion compounds and just dock all of them, right? So if you were to take that and say, okay, let me try and do only stage one, which is just the docking part, On a machine like Summit, which has 6 GPUs per node, we can dock about 15,000 ligands per second, right? And if I use all of Summit, which is about 27,000 GPUs, I still need about 6.8 to 8 hours to compute on a single protein structure. Then immediately you see the sort of issues that you get, which is that if I don't have a way to actually scale it up, then if I have to do it on 100 receptors, I still have to use all of Summit for at least a couple of days in order to get this. And at the end of the whole story, you might not have something that actually leads you to bind a molecule, but you might end up having something that's actually not even a lead. So instead of doing that, we said, why not use a machine learning model that can actually interface with the high throughput docking, whereby we basically say, instead of actually understanding whether the dock structure is right or not, which is basically to predict whether that protein would bind the ligand, we'll basically say, let's use the machine learning surrogate to say, is this molecule even valid or not for this protein? If not, we just throw it away. Then you have a very small subset of compounds on which you need that. So why is that actually helpful? If you look at this ML1 stage, we can actually get a bit of flops per second, and the throughput of the number of ligands is significantly higher. So if I can do only stage 1, which is the docking, physical docking, which is 14,000 ligands per second, I can actually get up to 300,000 ligands per second on a single GPU, which is important to note. That means that the entire library can within a span of several minutes in order to actually get a viable result. So in a consequence, what we said was, instead of doing this using a high throughput screening, we'll actually use machine learning to help us do this. And the idea for machine learning is actually something very interesting. So we are not predicting the docking scores at all. We are not predicting what that molecule is doing. Instead, we are going to predict what we call as a docking value, which is based on the ranked order of what that particular model looks like. So the ML problem formulation, instead of actually looking at the regression problem of predicting the docking score, we're going to say how many of these compounds that we find at the top ranking list, given some training data, is represented in the true data or true library that we have access to. And that idea actually resulted in this use of what we call as regression enrichment surfaces. So you have the top percentage of ranked predicted scores, which are coming from your surrogate machine learning model, versus the top Y% of the ranked computed scores, which are actually from your training data. And then you're comparing that world to actually say how much of these top values are captured by the top docked models. And if it were to represent the true distribution, you can actually say that, okay, as long as I'm capturing the top 10% of these molecules that are present in my larger library, then I'm doing a good job, because with that, I wouldn't escape any of these top ranked compounds, but I'll always keep them in my ranking list so that I know that I'm going into the next level. So instead of actually looking at this problem of predicting the docking score and trying to do some very complex math, we actually reduce that problem to be something more simpler, which is to keep only track of the true hits. And we leverage actually image-based CNNs to do that, and therefore they're quite, invariant to the formulations of rotation and translation, and therefore they give us like good results in terms of predicting what those molecules. So in terms of the computational performance, we can actually screen against all these receptors. You can see the amount of time it takes to do. In fact, compared to what we could do on Summit, this whole workflow could result in up to 95% utilization of the entire supercomputer, while actually giving us quite a few docking rates per hour. So in fact, you see we achieve like 11.3 into 10 power 6 docks per hour, compared to Frontera, which is about 27.5, which is a more recent machine. And therefore, this push on getting the machine learning to actually infer at very fast speeds was something that was very important from the beginning so that we could get the maximum benefit in terms of covering this entire chemical landscape, right? So the second stage of this is now to estimate something physically relevant. So right now, I only, yeah,
Arvind, if I can, I'll keep trying to wrap my head around it. Uh,
sure.
so you said that instead of actually predicting these docking scores, you're predicting a bound on the number of molecules that is needed. Is
You're
that
predicting the bound on the number of top molecules that are needed. So if I say, I want to cover 20,000 compounds, then I need to know how many docking calculations I need to compute before I truly have a representative 20,000 compounds.
okay? And what the part that I'm missing is that you know the number of computations, but uh, do you know which molecules to perform them on?
No, it is like sampling, right? So if you keep a sample of, if I randomly select these samples from the 4 billion compound, let's assume we are working with the 4 billion compounds, right? So let's say I pick up a random sample. I want to be sure that I've covered the top 20,000 with 95% accuracy. This is actually what we say as percentage of top Y% captured by the top X%, right?
Okay.
And if I am in this regime right at the diagonal side, you clearly see that you're not going to capture all of them, which is obvious because you're never going to be able to say, if I scan only like the top 10, I'm not going to get the top 10 from the 4 billion list. It's going to be much larger number. Mm-hmm. So in order to cover the best set of results, you want to be somewhere around these edges of the distribution, right? Around these areas where you clearly see the presence of, coverage, which is improved by the fact that you have a larger sample. Mm-hmm. Or you're able to cover a larger amount of the chemical space. It depends on the diversity. Mm-hmm. And that's what we are trying to say. Can we provide a quantitative bound? Because I'm not going to be able to dock all the 4 billion compounds. Sure. I'm going to be able to only choose certain numbers that I can get from, these libraries that are representative or these libraries on which I don't know what to do with them.
Yeah, but you know the number to sample or maybe the region to sample, but you don't actually sample them.
You don't sample them, yes.
That is taking care of later stage.
Yes.
Okay.
That is the part of the story where the machine learn the binding affinity. This is where most of the physics-based models actually play a role, which is you do these ensemble docking calculations as training data. You use the machine learning-based surrogate model to predict how many compounds should I dock. Mm-hmm. Once you get those compounds that are docked, you're now going to push it through a physics-based model to identify what compounds are actually like really truly representative of the binding set. Even in the top ranked ones from your docking calculation, sometimes they might just fall apart. They are just useless. They don't bind. They don't do anything. And so you want to improve that confidence in some sense, and that's why actually you resort back to your physics-based models to actually study them.
Nice, thanks. There's one question by Piyandu. Are you using other models like graph attention rather than CNNs? I'm not sure you're going to talk about this later, or you want to answer this?
No, I'm not going. So there are lots of models that are out there that actually predict the docking scores and things like that. Since we were looking at this sort of regression ranking, we really wanted to use the simplest possible model. But doesn't mean that graph attention networks are not useful or anything. We have tried them. We have had good experience with them. It's just that we wanted to be very practical about how long it takes for us to run, especially the training part. As you can imagine, graph attention networks do take a much longer time than CNNs to train, and therefore it was just a very practical choice of how we decided to do this.
Sounds good. Thanks.
All right. So once we do that, we get into this aspect of saying, how do we get access to free energies? And the free energy aspect of it is actually driven by two aspects. One is we need to run simulations at very long time scales. So if you want to estimate the free energy of binding, it usually takes at least several months of hard-bound computations on your supercomputer to actually get these numbers. And therefore, that's actually a problem. So the traditional way how these simulations are run, if you just look at the landscape, you basically see that you have your job scheduler, you run your simulation, you store your data, you analyze the data, visualize it, and do that. Unfortunately, this entire linear way of thinking, which is to do the submission of the jobs, run them, get the analytics, and then do the visualization, is unfortunately not sustainable at these new scales of machines that are out there. So what we had to do instead was to interleave these analytics and simulations together in such a way that we could get rid of this intermediate storage aspect. We're not going to throw away the simulation data per se, but it's only that we wanted to do the analysis online in some fashion that would allow us to look for features that we think are very important from the data and use that data to actually guide us in terms of, whether we have reached the right sort of, performance thresholds. So that very idea, something what is called as ensemble adaptive sampling. And in this case, what we are trying to do is we run a large number of these ensembles, which is, of the order of 10,000 to about 1,000,000 or so simulations. And it's a statistical approach. It's a weighting game that you have to play. But the ensemble methods are, driven by what we call as adaptive sampling techniques. I might not find time to actually tell you what adaptive sampling is all about, but the idea is basically you're exploring this conformational space, very complex conformational space in a simulation at very fast speeds by actually allowing to propagate in a direction that is most meaningful for the system of interest. And that's all driven by just the data analytics. So you're basically allowing the machine learning to make a choice of saying, who should I sample next? So the famous example for this is a very simple algorithm called as replica exchange. I'm not going to, again, touch base on that. But the idea is we are using these techniques to actually drive how simulations are run. So this is something that we developed in our group about a year back or so. This is called DeepDrive MD, where we use deep learning driven ideas to adaptively sample our machine molecular dynamics simulation. So you assume that your simulation tasks are running independently. The execution time is shown on the y-axis. And as you progress through time, you're collecting the data and training machine learning algorithms that basically tell you if there is a confirmer that is actually interesting. So if you're running an MD simulation, each of the frames, you can think of it as a large movie. Each of the frames represents some configuration of this molecule at given time t, and you want to say if that that molecule is, that molecular configuration or frame is actually interesting or not. And you use some sort of clustering or ideas around that to say identify these outliers in the data. And once you identify these novel states, you're going to run more simulations in terms of these interesting states and cull the simulations that are actually not useful. So you're going to iterate over this entire thing so you can actually enhance the sampling several orders of magnitude. And so there are two phases here. One is the learning phase where you're taking the data that's being streamed from the MD simulation, you learn on that data, and then you get into the inference phase where you say, okay, let me start new simulations from where I think it is interesting. Again, don't worry about the candle infrastructure. But why do we care about this? So AI-driven MD, especially in the context of protein folding, you might have heard that DeepMind actually solved the protein folding problem. In the context of protein folding, is at least an order of magnitude faster than traditional sampling approaches. So I don't think people would have heard of this machine called as Anton, which is a specialized machine for doing just molecular dynamics simulations. And if you look at the amount of time it took for them to actually fold a protein like BBA or VHP, it's about 124 microseconds of sampling which was needed. So that means that they were running this machine continuously for over a month to actually generate these data sets. So what happens with the DeepDrive MD idea is that there is a point where you can see a crossover from where the machine learning has actually learned enough of the sampling space and then completely accelerates and takes over the sampling part. So in fact, within 22.8 microseconds, we cover nearly 93% of what was covered in their original trajectory data. So that means you actually buy some time as a consequence of this. So, already there is a magnitude of difference, 124 microseconds versus 22.8 microseconds. So there is one order of magnitude approximately different. But if I were to use a pre-trained model, you would actually see that curve shift even further to the left, because you're now using only 10.8 microseconds of data compared to the 124 microseconds. You can actually push this even further to the left, which means that the crossover is taking on earlier, and then you're sampling even more of the landscape. So in some sense, we were able to sample almost 98% of all the states that were looked up in the traditional ways of sampling within just the first 10 microseconds, whereas they needed at least 102 microseconds or 223 microseconds to see the same level of events. So there are greater efficiency gains that we can get with larger and larger proteins, because this is something that you can actually quantify in the case of these protein structures. So we were able to do that, and that actually led us to actually implement, as part of our entire workflow that I was talking about, this idea of enhanced sampling that could be indicated with these high throughput docking. So without getting into the details of how we do these binding affinity calculations, what I just want to show you is the fact that we were able to take a bunch of these ligands. So these are some ligands that we were working with. L78, L6967, these are all coming from our libraries. And once you start looking at that, we can actually ask these questions in this latent space representation. Am I sampling far enough into the landscape in terms of actually looking at some interesting events going on? So in this case, especially with L78, there are two different events that we observed in the trajectories where we could see the presence of this ligand actually flip its tail on one side, and it also flips to the other side. So that means that it's quite flexible inside the active site. And so we needed to pay a lot of attention to how these molecules are interacting with each other. So in one case, the one that is indicated in the green box is the one that's actually favorable in terms of interaction. So it has to flip over in one way, and it should not flip the other way. So that's something that we'll have to work on in order to actually have a better binding compound. So as a consequence of doing this entire set of workflows, you can actually see, with respect to these coarse-grained calculations, we bring down this energy barriers significantly, especially if you look at 6939. When we started out, the energy was actually somewhere at around 62 or so. At the end of these fine-grained refinements that we were doing, we actually bring it down significantly to about minus 70 or so, which is actually a good thing, because we are now able to identify better binding compounds. So in some sense, these sampling techniques potentially lead to refining good versus bad lead compounds. It reduces the expensive computing steps that are involved in these binding calculations by about 4 to 20x. So this is actually a rough estimate based on a very small set of compounds that we did for this paper. But there are also a lot of enhancements that are going on with much larger data sets, and I think this number is about to increase significantly in the next iteration of this presentation. Right? So I just want to summarize some of these parts that we just spoke about for drug discovery. There's a vast potential of how AI models can be used for drug discovery when they're integrated with rigorous physics-based models. There are companies out there that are selling a lot of these toolkits and software for doing drug discovery by claiming they're doing generative models and things like that. But I would also be very aware of the fact that there is a physics and chemistry-based knowledge that needs to be exploited in terms of actually building better drugs. And as a consequence, many of these AI-driven companies that are actually doing these sorts of generative models and things like that are actually suffering at the back end, because they don't have a way to validate many of these models. So we have the ability to actually validate them, and I'm going to talk about that at the end of the talk, where we can actually say we have crystallized structures at the lab, and we know that why this compound would actually bind. And this is actually on the PL protease example that you saw. The AI models need to also address a few emerging challenges in the sense that if you look at this workflow that I showed you before, we are measuring ML models to actually come up with docking scores. We have the ability to sample these spaces using these latent space representations. But the unfortunate problem is they're not really that composable. So you cannot really string them together as AI models with easily exchangeable data interfaces currently. And that's something that we are very much interested in working. And then I'm going to talk a whole lot about scaling and integrating these AI-based physics models for HPC simulations in the next part. And of course, the last part, which I think is less addressed both in the community as well as in terms of our research also, is that we really do not understand the limits of the robustness of these AI models yet in terms of how we have worked with them. So something that we are very constantly checking with a number of our runs and trying to understand is how robust are our interpretations, as well as the fact that how robust are our predictions in terms of these. So tomorrow, I don't want it to be the case that I change my software from PyTorch to TensorFlow or TensorFlow to PyTorch, depending on which school of thought you're from. I just don't want my results to change because that would have a drastic impact in terms of drug discovery. So that's this one. So let's get into some of the aspects of scaling these AI driven.
Arvind, so it seems that you need both the simulations and the training to happen in parallel. There's no, the pre-training doesn't really completely take over. Even if you have a pre-trained model, you still need some of these simulations for some reason. I couldn't understand why you need simulations even after having a pre-trained model.
So this pre-trained model, if you remember, the way I was training my machine learning code was as the simulations are running. Right? The pre-trained model would have only seen a certain part of the landscape. It has not seen everything.
I see.
So, and I need it to propagate to a place, for example, let's say I need to fold the protein to a final folded state. I need to be at a point where I really understand that this is the final folded state and it's not going to change as much.
Mm-hmm.
In fact, this part that you see in the graph where we have terminated it at 93%, for example, or 87.5%, for example, is because we know that we have sampled everything. Right? And also the fact that, we had reached time limit on the supercomputer. So that's another side of the story, which is that we have to be practical of sample. But given a time bound on how much sampling we can do, we can claim what is the percentage increase in terms of with AI, without AI, and so on. So the fact is we need to sample after because we need to know how good we are in terms of the sampling ability and whether in scientific use case we really want to show we have folded the protein. Right? If not, there is no use for these algorithms, really speaking.
Mm-hmm. But with what I'm wondering is that as the model sees more and more simulations and more data, does it actually learn enough about the protein structure that it can predict the folding, whether it's a folded state or not, or it all needs to rely on simulations?
No, I think we have not shown that here, but if you read the papers that we talked about, we actually show you what it is learning.
Yeah,
right? We do show you what it is learning, and we can tell you very carefully that this is learning what we call as metastable states in the sampling process. Right? It does identify bottlenecks. It does identify misfolded states. In fact, this is done completely unsupervised. We don't even say this is a unfolded state, this is a misfolded state, this is like that, and this is like that. So we don't say that at all. We just say directly, go figure out for yourself as to what that is. And so this is done completely unsupervised.
I see. Okay. And since you said you can figure out what mechanism, what probing do you use to figure out what the model is learning? Is some kind of PCA visualization?
Yeah, you can think of it as a PCA visualization. We use TSNE to visualize. Right? TSNE to visualize much of this stuff because this is a non-linear latent space that we are talking about. So we use TSNE to visualize. I mean, we are also interested in working on other aspects of this visualization, which can help us better understand these spaces. But from our, three-dimensional view of the world, I think we are still okay with TSNE for now.
pretty informative. So before you jump into the next section, maybe 2 minutes break or 1 minute break.
Sure, I'm okay.
Audience
Yeah.
has been relatively quiet. So, do you guys have any questions? Uh, are you following along? Are you getting the gist of the talk? Please feel free. I know this is a problem that we face in every talk. It's a virtual medium, and even though everybody has questions, it's not very seamless. So, okay, so there's one chat box. Okay, Dibyendu asks, how will AlphaFold 2 like Algo help? Or can it help at all in this segment?
It depends on who you ask and when you ask this question. I'm probably at a state where I'll probably say things that are not appropriate. I want to keep myself neutral about what is happening with AlphaFold and things like that. I think there are certain advantages of using AlphaFold like algorithms. I think here we are not. I mean, I showed you protein folding because it's a more relatable example, right? It's a more relatable example for people to see why it is doable. But the protein folding example is not where we want to be. We are really into how we can predict drug binding, how we can understand how drugs bind to these proteins, and so on. And I think eventually, if AlphaFold were to evolve into a place where it actually understands the chemical space, that's where it should go. And I think that would be fantastic. And those things will actually help. And from our viewpoint, everything has to do with the fact that we wanted drugs that would work, which means drugs that we could crystallize, drugs we could see that it can input to other sort of machine learning codes, as well as the fact that we could validate many of our machine learning models through rigorous experimental data. And therefore, I think a lot of our work just went through that. There's another question here, which is, have recent advances in protein folding made course? Has it made it less relevant? I don't think so. So if you think about what Foldit and other portals actually did, the games like Foldit and so on, what they did was essentially crowdsource how people would think about protein folding as a game. Right, and you could also think of playing the protein folding as a game, and that's actually one of the ways in which people have approached it, which is to use ideas like reinforcement learning and things like that to essentially solve the game of protein folding using the same rules that are there in the game like Foldit. So if you look at Foldit, there are very simple moves that are all present there, which are physics based, by the way, and then they're interacting with those things to actually give rise to compounds on aspects of how the folding actually proceeds. So I don't think they become less relevant because these protein folding games, especially the ones that Foldit has, they do record all the user moves to actually come up with a way to this one. So it's definitely possible to learn everything that you want to do from those trajectories, really, the game trajectories. So they don't become irrelevant at all. So how is the input given to the first? No, could you share your input data? So much of the data and everything that we are doing currently is, as I shared on the website, everything is out there. You have to go, if you search for the NCOVE group 2019, you'll find most of our input data as well as the model code and everything. So that's easy to find. How is the input given to the first CNN? Is it atom-wise or molecule-wise? Is it 2D or 3D? So surprisingly, Sunny, the model is essentially 2D. And they are rotation invariant models. So we use them because they are the most practical way. The 3D models really do not buy until and unless you put energetics into it. So energetics are extremely expensive. So we need something like quantum mechanics to actually come up there and do something if we want to get it right. So we just do a 2D image input, and it's surprising how well the 2D image inputs actually do. Yeah, in my next part of this presentation, I'm going to talk a little bit about how we are using AI accelerators like Cerebrus on running some of our codes.
It's great. Great set of questions. Okay, sounds good. So I think we can continue with the next part of the talk, or as you want to take a break also, that's also fine.
I think we can continue. Right?
Okay.
All right. So let's talk a little bit about how we have been trying to scale these workflows. So in the previous part, I just conveniently swept off everything under these simulations into this idea of doing deep drive MD. But the real hard part is actually saying you have MD simulations that are running constantly, and these data sets actually need to be streamed into our deep learning or artificial intelligence tool sets. And we need to get those states that are being sampled, understand which states are not important. So, for example, you terminate the ones that are not interesting here. And the ones that are interesting, we continue running those simulations as much as possible. So, until you saw the previous ones, it was all assuming that the simulations and learning can go in parallel, and assuming that there is some data latency in terms of the generation. But here I'm going to talk about the true streaming application of it, where we are running simulations on our GPUs or Theta GPUs, which is an A100 cluster. And that data is actually being streamed onto Cerebrus CS1, where we will do the machine learning and the artificial intelligence code, and eventually track it back to these for running more simulations. So the idea behind this whole thing was that, if you dissect this whole idea, you can actually think of taking the MD simulation data, you build an input contact matrix, you run your deep learning algorithm. In this case, it happens to be a variational autoencoder representation. And that latent space representation, as you can clearly see, clusters the data on the basis of some physical parameters that you can track from either experiments or from simulations themselves. And then you can cluster these conformers to actually see what sort of populations you're exploring. And once you do that, you can say, okay, if there is an outlier that I detect, which is kind of interesting, I'm going to start these runs separately and cull the simulations that are not productive. So this is the sort of workflow that we needed to implement somehow in such a way that we could run them. So there are some computational challenges involved in this, which is that if I were to do this input contact map representation, which are sparse matrices, unfortunately, the number of parameters I train for even a relatively small protein, like the spike protein that I was talking to you about, is about 1 billion parameters. Ain't happening on the current GPUs, right? Again. And so we actually say that, but we also show that it's possible to do. So the spike protein is about 1.5 million atoms. We can actually modify the VAE architecture to implement larger systems and implement this entire architecture in a model parallel version using PyTorch. And that actually improves the performance of the layer-wise adaptive scaling and things like that. So if I end up doing this with GPUs, with one GPU, I actually get a batch size of 8, which is still small, which is not a good idea. But, you can still show that it works. With 2 GPUs, I can get a slight reduction in the numbers. But this is actually the problem, which is that I still have 1.14 billion parameters to train. And it's not a child's play to actually go there. But if you do that right and you're able to train it for such a long time, you do see that the learning actually culminates in some sort of clustering, and you can see that there are several outliers in the data, and I can use these outliers to sample more interesting features from my landscape. But the important thing is we can actually learn what is going on in our simulations. So in order to actually overcome that parameter problem of training, we said, okay, in terms of reducing this algorithm, we are still going to use autoencoders, which are still very powerful, but we'll actually put them as adversarial autoencoders, which allows us to do efficient analysis of this. So I'm not going to talk about adversarial autoencoders and things like that. I think it's just too much of depth in terms of what we are trying to do. The idea is you still have your encoder and decoder networks, but at the end of it, you're just providing it with the discriminator that samples from a prior distribution that we know does provide valid confirmers, and basically say if a new confirmer that I'm observing is actually novel or not. That is it actually a real confirmer which is good or something that is unphysical? So instead of working with these contact matrix representations that I was talking to you about here, we decided that we're going to directly work with coordinate representations, what are represented as point cloud representations. People in the imaging field know this very well. So we work with the 3D coordinates directly from our simulations and build these adversarial autoencoders, which thankfully for us ended up reducing the number of parameters from about 1 billion to about 10 power 7. It's still 10 million, still a large number, but actually doable on a computer. So if I were to take this and look at the computational performance, the VAE actually requires larger memory footprint and longer training times for the same size of the system. So this is again the spike protein where we actually look at the spike monomer, spike dimer, and spike trimer. You can clearly see that there is a quadratic increase in the amount of memory that is needed. The training time is also increasing quadratically. On the other hand, if I look at the adversarial autoencoder, it doesn't really depend too much on the size of the protein. So the training time per epoch pretty much remains constant over the course. It's slightly increasing, but it's still pretty much compared to what we have with the variational autoencoder, it's pretty much flat. And in a similar fashion, you can actually see that the memory consumption is linear instead of actually being quadratic. So which actually helped us push the boundaries of what we could simulate. So when you take a look at the spike protein, there are some interesting movements that we are trying to track. Here, I'm going to plot these in terms of the root mean squared deviation from the point of view of what we call as snapshots of the spike protein, which I was showing to you from the beginning, where I'm just going to track the motion of this particular area that's highlighted in blue. Right? And as a consequence, when you observe a little bit about how this latent space is represented, these are simulations of over 100 million snapshots, which have been summarized here over the course of our data. And if I were to stop here and look at some of the intermediate points, so I'm just going to highlight something there, you could actually see something very interesting going on, which is that this region that I highlighted in blue before has started to open up completely. Right? And that's a sort of information that you would really play into while trying to understand the sort of motions that you want to capture from our data sets. So in this case, we are now sampling many of these open state simulations where you can see this yellow point, which is about 10.5 angstroms away from the original starting state. And that's actually kind of a very big deal for us because now I can actually shrink the space out and start asking questions related to the biological function of this protein. So here you see the entire protein in its view. What I showed you was this part before. Now I'm going to shrink all of that conformational space. And in the learned space, I'm going to take these new simulations and embed them and learn what's going on from them. So this is just an inference phase where you can see that I'm plotting all the conformations from my simulations. And then I'm actually allowing it to tell me where should I pay attention to. And as a consequence, you can actually see that there are some very interesting movements that are going on in the protein, which have nothing to do with the rest of the molecule. It just has to deal with the fact that this stalk region that I'm highlighting here with my mouse pointer is actually changing its conformation. Of course, this is something that we learned through many mistakes. Right? But the fact of the matter is we can actually track these sort of large-scale changes in this visualization space in the inference stage, where we learn that there are a lot of these fluctuations that can characterize what's going on. So why was this important? In fact, what happened is the fact that when my collaborator, Romy Amaro, were trying to understand how does the spike protein interact with ACE2 receptor? So this is the first step of the infection I was talking to you about. In the first step of the infection, if you were to look at what has to happen to the spike protein so that it can actually bind to the human protein, there are a bunch of motions that have to happen. So it has to get this RBD region up, which was this blue region that I showed to you before, right there, right here. That has to completely unfold and actually do something more. Once that happens, the spike actually has to compress on itself by bending. So the knee motions are actually important for that. So in terms of this particular side of the story, in their original simulations, replicas 1 to 3, they were only able to sample about 35 degrees of this knee motion. On the other hand, when they used the AI-based method and said, okay, let's take these outliers and start simulating from these set, which is replicas 4 to 6, we significantly pushed the boundary of what they could sample. So in some sense, we could measure the effective speed up of approximately 8.3x sampling efficiency without DeepDrive-MD, which was zero point 0.5 microseconds, but with the DeepDrive-MD, within just 60 nanoseconds of sampling, we could actually get to the same thing. So we observed over 25% more conformations in the knee bending in just 12% of the time. So that's a big gain for when you have to like sample on these very large data sets, right? And that motion brings us to this idea of how we are using Cerebrus now. So this is actually a machine where it's a 15 rack unit system, 400,000 AI optimized cores, 18 GB of on-chip memory, all clock cycles from the cores, 4 billion parameter trainings can be done, 9 petabytes of memory bandwidth, and obviously this sort of thing can support TensorFlow or PyTorch and things like that. So, of course, we worked with our colleagues at Cerebrus to actually think of how we could couple the two systems together. So we have the Theta GPUs, which are basically a GPU cluster, like DGX cluster. And these DGX boxes consist of 800 NVIDIA cards on which we can run our simulations quite efficiently. But we write the frames onto the secondary storage device, which are fast hard drives, and transfer all the frames in a asynchronous manner to our Lustre file system. From there, we transfer much of the data back to this CS1 so that we can dispatch the training and run them. So what it does is essentially, I showed you this protein that we folded, what was called as BBA. We could actually fold this entire protein in less than 2 hours. Right? So a simulation like what Anton did, which took a couple of weeks to run, versus a couple of days to run on a supercomputer to actually get it to fold like the way we did before. And now with coupling to the CS1, we can actually fold it within 2 hours. And the fact of the matter is, as we increase the batch size and keep the learning rates, we do achieve very strong convergence, and it can process up to 48,000 samples a second. That means that the inference is just like this. It just, you send the data, you get it back. You don't even understand the difference in terms of how much you have to wait. And so what we're tracking here is the evolution of the root mean squared deviation that I told you. And so we do sample a lot of these native state conformations at the end of the 39th iteration of this whole process. And the fact that we can do this in under 2 hours for us was actually like very helpful. And now we can ask more interesting questions related to how we can bind two proteins and sort of understand if you were to just do equilibrium MD simulations versus this sort of a streaming simulations, how much of conformational diversity we can sample and what sort of things that we can put together. So the idea was basically, this allowed us to demonstrate the first time, I think, to couple how AI-based simulation techniques can actually evolve into something that can be coupled on heterogeneous hardware. And this idea of coupling heterogeneous hardware, again, I'm not a performance person, but we care about the fact that we can do a whole lot of these simulations at the scale that we want to do, especially in the context of SARS-CoV-2. And how has it impacted this medical therapeutics project is essentially the fact that we were able to screen about 1,000 compounds for which we were able to do whole cell assays, of which 50 of these compounds actually show viral inhibition activity. So if you just imagine, getting 50 compounds from the top 1,000 molecules, usually the number, if you were to just do plain docking, is 0. Right? But in terms of this entire workflow, we were able to identify at least 50 compounds that show the ability to inhibit the virus. And many of these compounds have actually been crystallized at Argonne, ORNL, as well as NSLS2, which is Brookhaven. So these compounds are very important because now they give us ideas of what are the new compounds that we can go after. These are not molecules that eventually become drugs, right? That's a whole step of things away. But the fact of the matter is we were able to screen them. We were able to successfully identify that they do bind to the protein of interest. And the fact that we could point where we could understand what sort of interactions exist. That was the most important thing for us. And I think we were happy to do that. And now what we are trying to do, we do have synthetic chemistry being driven across the labs to optimize so that we can become more specific towards the target. This is all coming from compounds that are commercially available. We can order within 2-3 weeks and do a sort of example tests and runs and things like that. But we wanted to be at a point where we could do some more interesting work, and that's why we are going the route of synthetic chemistry. Just to give you in terms of the scale of operations.
Right? There's a quick question.
Sure.
How much did the scaling improve? And there wasn't any scaling from 1 GPU to GPU with VAE.
Yeah, those experiments are being run, so you I cannot talk about it because of limitations with what we have at Cerebras, but you will see those numbers very shortly in a conference paper. So as soon as I upload it, I'll definitely talk about it. Sorry.
That's fine. Thanks.
So
there is a gap between discovering these compounds and actually making drugs out of them. Is that?
Yes, there is a huge gap actually. I mean,
could you summarize that?
So once we discover that we have a hit, which is what is done in the crystal structure and so on, a true hit, I'm sorry, not a hit, but a true hit. What happens is medicinal chemists have to go in and start working on these compounds to say, are these true representative molecules that don't have any other human proteins on which they bind to? Mm-hmm. That's a very important step.
I see.
The next step is actually to make the compound non-toxic, which is, there are cellular assays that they do on human cells as well as other cells to try and understand if these molecules are cytotoxic. So they shouldn't end up killing cell, or killing any healthy cells. So those sort of texts, this one's happen. Then there is the question of the blood-brain issues and things like that. And then there is a whole lot of screens that are done to make sure that these are truly safe and they won't inhibit anything that is going on in the body. And then after that, it gets into clinical trial.
So this naively wondering that many of these steps sound like, can they be done computationally too with simulation, or that's just too?
No, unfortunately, many of these things cannot be done using simulations directly. Yes, simulations can aid a few of these things directly, yes, no doubt, but they cannot be done because you need to understand all of the physiochemical aspects of a particular molecule against cell lines, right? Against cell lines and also in living organisms. So you have to do that on, it goes through a whole bunch of things, which, is just a whole nightmare. And that's one of the reasons why a drug takes so many years to come to the market. The fact is, we want to compress even this initial part that I was talking about, coming to the hit identification, right? Usually takes 2 to 3 years.
I see.
And we wanted to compress that entire timeline to about 6 months if possible. Right? And here is one way to demonstrate that it's possible. And there are other groups that have done similar work and they have actually been successful in a similar manner. They're companies, not companies, but what is called as a COVID moonshot in the US, which has been working tremendously. And thankfully, they're also working with us. So, we have been very fortunate to actually collaborate with so many different groups and people. So it's just been a tremendous effort on everybody's part. and we are exchanging compounds with them. They're exchanging compounds with us. So there is a whole bunch of steps that are going on to make sure that our assays are reproducible, their assays are reproducible. I think there is a whole lot of community-wide recognition of how important this step is. And of course, this is just the beginning in some sense for a lot of us, because this virus is not going to go away. Right. So that's that. I mean, as tragic as it sounds, is the reality of the matter is that it's going to be something similar to the flu that is going to return in batches. Hopefully, not in the same level of mutation that we observe. So hopefully, we can be careful. But
Yes. Okay. Sounds. Thanks. Yeah.
cool. So I didn't write this here, but the scale of that we have done for these spike protein simulations is approximately 2.2 zettaflops. Right, that's about 10 power 21 computations that we needed to do to get it to that point where we could understand what was going on. And we computed nearly 1 billion docking calculations using OpenEye as well as Autodoc. And these are mostly based on open source software tool sets and thousands of deep drive MD calculations over multiple platforms. And complete extensible computational infrastructure, which is based on open source toolkits, which we could essentially get full peak performance on a machine like Frontera. Of course, Frontera is smaller than what we have on Summit and other machines, but this is still a significant thing that we could achieve 95, 97% core utilization of these machines. So, we have been quite happy to do that. Of course, as I said in the beginning, this is not possible by one person or 10 people. It's just a team of more than 300 people with whom we had to coordinate and work on. And of course, the computing support was provided from the leadership computing facilities, both Argonne and Oak Ridge, Texas Advanced Supercomputing Center, San Diego Supercomputing Center, Indiana University Computing Center, as well as the HPC Consortium, of course, funding through Argonne, as well as the DOE and the Exascale Computing Project for cancer. So all these things have helped us a lot. And with that, I would like to thank you for your attention. If you have any questions, feel free to shoot me an email or ask me.
That was an amazing talk, spanning several dimensions of computer science and biology. Very, very thankful for that you had to give this talk, and I believe the audience must have been very deeply informed about this. If somebody has any questions, please ask them. I think this is really very, very covers so much span that might take human simulations of several days to absorb.
Oh God.
Content. So please, if somebody has any questions, please shoot them.
Thank you.
All right, so let me again thank Arvind for
Thank you.
time to give this talk to our audience, and thank you for the audience for asking great questions. So let's conclude this session. Thanks, Arvind, again.
Thank you so much. Thank you then. See you.
See you. Thanks.
See you, Nishant. Thanks.
We have more such talks planned, and you can visit our YouTube channel where this talk will be available. Arvind, would you like to share the slides? The talk video is going to be there anyway.
Yeah, video would be there. Okay. I'll try and share my slides. These are like really, really large animations and everything together. So it's more than 600 megabytes or so. I'm happy to share, but that'll be the issue.
So we'll see about that. But till then, the video is going to be there, and people can listen. Cool. Thank you, guys. Thanks for joining this morning, this evening.
good night
Yeah.
to most people, right? So